So in this lesson, we have been using our estimate, the 95%, fall within two standard errors. However, if you recall from the lesson on normal distribution, this is just an approximation. To be more precise, I need to use the inverse normal function on the TI-84 StatCrunch. We could look it up in a table as well. And I've done this with the standard normal curve with a mean of 0 and a sigma of 1. So instead of stretching out two standard errors for 95% confidence interval, a better estimate is 1.96. And this is called the critical value. So for our tattoo example, we would get our margin of error would be 1.96 times the standard error of the sample proportions, which leads to 1.96 times 0.043, a slightly less margin of error, 0.084. And plugging this back into our our pattern of point estimate plus or minus margin of error gives us 0.24 plus or minus 0.084. Adding and subtracting, we get that we're 95% confident the true proportion of those with at least one tattoo is between 15.6% and 32.4%, a slightly tighter interval. So what if I wanted to be more certain about the true proportion? Maybe I wanted to be 99% certain that my interval contained the true proportion of those with tattoos. What could I do? Well, I would need to go out more than 1.96 standard deviations. I would need to go out some unknown standard deviation. Let's say if it's 99%, I need to look this value up here, right? We need to find that area that I've indicated there in the lower left corner. So we do it the same way we did before with 95%. We're going to say, we have 99% contain that middle part, so we know that 0.01 is left for the tails, for both tails. So we divide by 2. And we get, using the inverse norm function, we get about negative 2.576, and we'll discard the negative for the critical value. So for 99%, the critical value, we will recognize this again as Z star is 2.576. Some texts, for some reason, will use 2.575. Maybe it's easier to remember. So back to our tattoo example, we would say the margin of error is 2.576 times the standard error. This will give us 0.111. So again, it's p hat plus or minus 2.576 times the standard error, which is 0.24 plus or minus 0.111. We crunch this out, we're going to get our interval between 0.129 and 0.351. So again, we are 99% confident the true proportion of those who have at least one tattoo is between 12.9% and 35.1%. So notice that in order to be more confident, our interval widened. This is an important concept. And hopefully, once you go through a few of these, that'll just sort of make sense. Well, of course it'd have to widen. I mean, the more confident we want to be, the larger the margin of error. I mean, we are 100% confident the true proportion is between 0 and 100%. But that's not very helpful, is it? So there's always this sort of tension, this sort of tug and pull between the size of the interval and the level of confidence. So while we can use the calculator to determine this interval by using the inverse norm function, it's sort of nice to have these three critical values for intervals in your brain. And that is the 90% confidence interval has a critical value of 1.645. 95% we found was 1.96. 99%, 2.576. Now often notationally this will be expressed, the critical value will be Z star or Z alpha over 2. So alpha is that what's left in the tails, and since we have two tails, we divide that by 2. So let's break down that margin of error part of our formula again. So point estimate plus or minus margin of error. That margin of error actually is made up of two parts, right? So it's the critical value times the standard error. And so this is our sort of our general form for confidence intervals, no matter what the statistic is. In our case, it's a point estimate with a population proportion, but it can be anything. Means, two means, and we will look at those later in this module. Using symbols, we're going to have p hat plus or minus Z star times the standard error. So again, we're going to summarize. We have point estimate plus or minus margin of error. And the margin of error we broke into two pieces, the critical value times the standard error. And we saw symbolically, it was p hat plus or minus Z star times SE sub p hat. And again, recall what SE sub p hat was. It was the square root of p hat times 1 minus p hat all over n. So this will give us, plugging in the formula that you want to write down and sort of put into your heart, right? P hat plus or minus Z star times the square root of p hat times 1 minus p hat all over n. It looks crazy. It looks maybe spooky, a little scary. We'll work through a few examples and you'll see that it's not that bad. And ultimately, you will be able to use the calculator for these, but sometimes if you're taking the AP test, they will leave it in this form. And so it's nice that you can just go straight to this form. So the same conditions that we determined for the sampling distribution of p hat back in the earlier module, when creating a confidence interval about a proportion, we have to have a simple random sample, our 10% condition, right? So our sample must be less than 10% of the population. So our sample can't be too big, but it also has to be big enough. It must be large enough that we can use the normal distribution to approximate the binomial. So both n times p hat has to be bigger than 10, and n times 1 minus p hat is greater than 10. Let's check this out with an example.